Hey, how's it going, everybody? So we're just gonna go through right now and do a couple practice problems from one from chapter 21, one from chapter 22. So I just put my constants here. We have the elemental charge, 1.602 times 10 to the negative 19 coulombs. So this is the charge of either a proton, if it's positive, or an electron, if it's negative. And then we have epsilon naught, and we have K, which is 1 over 4 pi epsilon naught. So let's get started with problem 17 from chapter 21. We can see in part A, we have two charges. They are separated some distance d is equal to 1.5 meters. And each charge is Q is equal to 20 microcoulomb, which is equal to 20 times 10 to the negative 6, or 2 times 10 to the negative 5 coulombs. And in part A, we want to know the magnitude of electrostatic force on particle 1 due to particle 2. So F12 is equal to something. And so we're going to use Coulomb's law. Right. And if we want, we can do the vector form, but we're just asking for a magnitude here. So that's all we'll worry about. And so we can say F12 is equal to 1 over 4 pi epsilon naught times Q squared, since Q1 is equal to Q2, and then that's over D squared. Okay, and plugging in, we get 1 over 4 pi epsilon naught, which is 8.99 times 10 to the 9 Newton meter squared per coulomb squared. And all these constants are something that will be on an equation sheet for any exam or anything. And so then we can multiply that by 2 times 10 to the negative 5 over 1.5 coulombs per meter squared. Okay, and just taking a look at this, we can see we have coulombs squared and coulombs squared. Then we also have meters squared and meters squared. We're looking for a force, and we have units of newtons, and so we're all happy. Right, quick little sanity check. Pretty hard to get to the right answer and have horribly wrong units. Like, if your units are good, your answers has a better chance of being good. And so let's go ahead and pop this in the calculator. Times 10 to the 5th divided by 1.5 squared. And we get 1.598 two repeating coulombs, or we can say, oh, that's not coulombs, that's newtons. All right, and there we go for part A. Okay, part B, get a little trickier with it. Now we have a third particle brought into the mix. So we have particle 1, 2, and 3. We still have D is equal to 1.5 meters. And Q is equal to 2 times 10 to the negative 5 coulombs. All right, I think that's about all we're working with. Cool. And so now we want to find the magnitude of the force on particle 1. And so that's going to be equal to the force on particle 2, or the force on particle 1 from particle 2, plus the force on particle 1 from particle 3. And then since we want the magnitude, we can say F total, I guess, is equal to, I'll make that a T instead of a 1. I like F total better than F1. It's going to be equal to F12x plus F13x squared plus F12y plus F13y squared, all of that square rooted, right? Essentially what we're doing here is we're finding the vector components, and then what we're going to do is Pythagorize them to get to the magnitude, right? And so you have both of these in I hat, both of these in J hat as your two vector components, and we're having a good time. And so let's go ahead and say we have a traditional coordinate system. And so I think there's 1, there's 2, here's 3. And so just looking at this, we can say F12 is equal to F12y j hat, right? All of F12 points in the y direction, or j hat. And so then we can go ahead and say, let's switch over to green for no apparent reason. Contrast, whatever. F12x is 0. Okay. And so since we know F12 is going to be equal to the magnitude of F13, right, because they're separated the same distance, and the same magnitudes of charge involved in each. Right, with the idea being that F13 is going to be pointing this direction, right? So again, along the line that connects the two, and then since they have the same sign charge, it's going to be repulsive, and we point away. So we can go ahead and say F13x is equal to F13 cosine theta, where this angle here is theta. And then we can say F13y is equal to F13 sine theta. And so let's see what we can do to find F13. There's shortcuts we can do. But we could also just say, look, we have this triangle, we have theta, we have, what do we have? D over 2, we have D, we could do sine and all that. Or we could say, since it's an equilateral triangle, each angle is 60 degrees, and so theta is going to be 30 degrees because it's half of that. And so theta is equal to 30 degrees. Right. A little easier to skip the trigonometry when you can. That way, you don't have to bring SOHCAHTOA into your business. Okay, so getting back on track. Not that we were ever off track. So magnitude of F total is going to be F13x, which is going to be 1.6 newtons times cosine 30 degrees, plus nothing squared, plus F12y, which we all agreed was just going to be the magnitude of F12, so 1.6 newtons, plus F13y. I almost started writing F13y. This is number time. 1.6 newtons times sine 30, which is, of course, 1/2, squared, and then all square rooted. Okay, and so we can go ahead and plug this into our calculator, and we get let's see, let me just go 0.8 plus 1.6, 2.4, 30 cosine times 1.6, 1.38, but that's squared. So we have 1.92 plus this is also squared. 2.4 squared is equal to 5.76. We get 7.68, and we square root that. Well, this is just not a true equation anymore. And so we have the square root of 7.68 is equal to 2.77. 1, 3, whatever. And so we can go ahead and say the magnitude of F total is, well, roughly equal 2.77 newtons. Right, and so I don't think anything in this chapter is different than anything we did last semester, except for now you hit it all with, Coulomb force. Right, other than that, it's just you have forces in different directions, different magnitudes. You play your games with those, you get to your answers. Right, so cool. Got that one done. All right, cool. Let's go ahead and hop on over to chapter 22. And the 19 ran away. That's a horrible 9. That's not great either. Okay, so problem 8 from chapter 22. We have 4 particles, all fixed in place. And we are given Q1 equals Q2 is plus 5e. Q3 is plus 3e. And Q4 is negative 12e. So, and then D is equal to 5 micrometers, which is just a shorter way to say micrometer. And so the first thing this problem makes me want to do is turn it, right? I mean, we could, if we really wanted to, say like, haha, this is X, this is Y. But what we're going to do is just say this is our setup now. D, 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 some point P. Switch this up a bit. Plus 5e, plus 5e, plus 3e, negative 12e, X and Y. Which is the exact same thing as just changing the coordinate system, right? Like, we didn't do anything different. It doesn't, retain rotational symmetry. Okay, so what are we being asked to do? What is the net electric field at point P due to the particles? And so we can go ahead and say we want magnitude. Right. Or if you want, get a little fancy, you could write like E sub P is equal to that, right? Doesn't that look a little bit better than writing words in the middle of it? But, it's all fun either way. So, what is the magnitude of the net electric field at point P due to these particles? So that's going to be, we can go ahead and say E sub P is equal to E sub X I hat plus E sub Y J hat. Right, so I might as well go ahead and put Q1, Q2, Q3, Q4. And so we can say E sub X is from Q1 and Q2. Right, and then we can say E sub y is from Q3 and Q4. Right, because we can go ahead and take a look at this. That's not the one I wanted, but it's okay. I guess I'll use a little sparkly pen for a second. Right, because along Y, all we have is Q4 and Q3. And then along X, we have Q1 and Q2. So we can kind of group them in there. And already looking at this, you know, what do we expect to see from the electric field due to Q1 and Q2, right? Right, so Q1, it's positive, so the electric field points away from it, and it has some magnitude at point P. E1, why am I still using this color? This is outrageous. E1 is equal to K Q1 over D squared. And we can make this a vector, and it's pointing in I hat. Right? And it's positive because it's pointing to the right. And then when we get, I guess we're going back to that one, Q2, right? It's a positive charge, so the electric field points away from it, so it's going to be pointing to the left. And so we can say E2 is equal to K Q2 over D squared, right? And we're just using the formula E is equal to F over Q is equal to K right, E is KQ over R squared, right? And so back to E2. And so this is also in the I hat direction, but it's negative since it's pointing to the left. And so if we add these two together, we find they're equal and opposite, and we get sum of the electric fields in X is equal to 0. Right? And that looks reasonable, right? And so now we can just say, well, we can go, therefore, that's what those three dots mean, if you ever see those anywhere. E at point P is equal to EY. And you know what, if we want, we can go ahead and make those vectors, and that's still true. What a time to be alive. And so we can say E sub Y is going to be equal to E sub 3 plus E sub 4. And let's take a gander what we expect from these. Back to our trusty old whatever color this is. So we have our point P, we have Q3, and we have Q4. And so what do we get? Q3 is positive, so we expect the electric field to point down. Q4 is negative, and so its electric field points towards it, right? And again, you know, these continue on, but I didn't want to overlap, right? And this Q3 as well, right? Me explaining I didn't want it to overlap as I overlap it. That's, you know, what a strategy. Okay. And so we expect E3 to point down and E4 to point up in the J hat direction. And so we can say E3 is going to be equal to K Q3 over D squared, where E4 is going to be K Q4 over 2D squared. And we square the 2, we get 4, and then D squared. Okay. Now let's go ahead and make these into vectors. So this j hat, it's pointing down, so this gets the negative sign, right? Little sneaky there. Positive particle now has the negative sign on it. Whoa. Well, the electric field from the positive particle has the negative sign, right? And E4 will be pointing up, so all we have to do is add the j hat and the vector sign, and we're good to go. And so if we want, we can say E sub y equal EP is equal to E, we'll do E4 plus E3, so we can kind of subtract in the middle. And so we get K Q4 over 4D squared minus K Q3 over D squared. And so the other thing to keep in mind here is, since I already figured out the directions of the fields, I don't have to keep the charge as positive or negative. That I can treat them all as positives because the minus sign was taken into account doing this. And it is a little counterintuitive. The positive one got the negative sign and the negative one keeps the positive sign. But that just has to do with how we define our coordinate system, and the direction of the electric field is dictated by the charge, but you can have a positive electric field from a negative charge because you're defining the direction as being positive or negative, not the charge anymore. Okay. And so we get K over D squared times, let's see what Q4 is. Q4 was the 12E, so we have 12E over 4. And then we have minus the positive 3E. And so we get E sub y is equal to K over D squared E times 3 minus 3 is equal to 0. And so we get net E field at P is 0. Or if we want to be, very specific, E sub P magnitude. Okay, and there you go. All right, thanks for watching.